Let's now have a look at parameterized algorithms. So let me tell you a story. So let's say that a computer scientist meets a biologist. And so the biologist has done a few experiments, actually many experiments, around 1,000 experiments, but then he notices when he looks at his data that unfortunately there are some conflicts. So these experiments are very expensive to run, so he doesn't want to run the experiments again, but he just wants to filter out some of them that caused these conflicts. So he assumes that maybe 20 went wrong, and that's why he has these conflicts. And now he approaches the computer scientist and tells her, listen, I have these 1,000 experiments. Unfortunately, I can't use the data because there's some conflicts. So can you help me in filtering out some small number of experiments so that the remaining experiments are conflict-free? And the reasoning is that, well, if there's actually much more than 20 that cause these conflicts, then basically his approach is unviable and he needs to start over. But if the computer scientist can find around 20 experiments that can be filtered out so as to make everything conflict-free, then she has solved the issue of the biologist, and he can then use his data. Okay, so let's say n is our number of experiments, like 1,000. K is the number of experiments that we assume failed, so at most 20 of them went wrong. And now notice that the problem we want to solve, so can be modeled as, again, vertex cover. So we could have one vertex for each experiment, and then an edge between two experiments or between two vertices when there's a conflict between these two experiments. And now if we can find k vertices that covers all the conflicts or all the edges, that means that while removing these k vertices from the graph, removes all the edges of the graph. So it removes all the conflicts. So if we can actually find a vertex cover of size 20 in this graph where the nodes are the experiments and we have an edge between two nodes when the corresponding experiments have a conflict, then we can solve this problem. So, okay, so we saw that subset problems have these brute force algorithms. So we could do a brute force algorithm and say, well, no, wait. So the first thing we could do is we could prove that the problem is NP-hard. And then we could say, okay, the problem is NP-hard, so it's really difficult to solve. So using a computer to solve this will not get you anywhere. So that's what computer scientists did in the 70s. They basically showed a bunch of problems in some very interesting application areas are NP-hard, and then they went away. Then afterwards, they started doing approximation algorithms, and nowadays we do many different, we use many different approaches to solve these NP-hard problems. So including parameterized algorithms and exponential time algorithms, heuristics are often analyzed. So what can we do now? So the brute force algorithm, the 2 to the power n algorithm, would need something like 1.07 times 10 to the 301 instructions to actually get a result. So that's way too many because, well, let's assume the biologist has a slightly older computer, so he can solve 2 to the power 36 instructions per second. So this gives him a real world running time of something like 4.9 times 10 to the 282 years to solve an instance on 1,000 experiments. That's way too much because, well, the Big Bang happened roughly 13.5 times 10 to the 9 years ago. So waiting for 10 to the 282 years is definitely not an option. Okay, but we can be a bit smarter. So because we know that we don't need to look at all the 2 to the n subsets, but looking at all subsets of size k is enough, right? So if we use this reasoning, now we can get an n to the power k time algorithm. That's still a lot. So we still need 10 to the 60 instructions, which is still in real world running time much more than the time that has elapsed since the Big Bang. It would be much more useful to have a running time that where the exponential factor doesn't depend on n. So like in the last running time here, 2 to the k times n, the exponential factor only depends on k. So 2 to the k times a linear function in n. So if we could get such an algorithm, now we only need 1.05 times 10 to the 9 instructions, which is much less than a second in real world running times. So this shows you really the difference between something that's where the exponential factor depends on both n and k, like n to the power k, and some running time where the exponential factor is some constant to the power k, like 2 to the k. So even if we had the linear factor here, we get a very nice running time. Okay, so that's our goal here. We want to confine the combinatorial explosion of the running time to the parameter k. So this exponential part of the running time should only depend on the parameter k. And then we can ask questions like, for which problem parameter combinations can we find algorithms with running times of the form some function of k, so some f of k, times a polynomial in the instance size. And here this f just needs to be a computable function of k that's independent of the input size n. So our goal is to study which problem parameter combinations have these kinds of algorithms. Because for one problem, we could have many different parameters. So we could have, for vertex cover, we could have the parameter k, so the size of the vertex cover we want to find. We could also have some other parameters, like the largest degree of the graph, or maybe the tree width of the graph. And so here are some parameters that are used quite often. So one is the input size, which is a trivial parameter. The solution size is very popular, like the size of the vertex cover. But also structural parameters that are related to the structure of the input. For example, the maximum degree of a graph, the tree width that measures how close the graph is to a tree. We have a whole lecture on tree width, so we'll get more into depth on the tree width parameter. And there's related parameters that are called branch width, genus, and click width, and many others. So now we look at parameterized problems, and they're so it's a decision problem. So we have an input, which is an instance, and we have a yes/no question. But now in addition, we have a parameter. Like parameter, generally it's called k. K is usually the name of the parameter. And now we can look at complexity classes in parameterized complexity. So P is the standard class of problems that can be solved in polynomial time. But now there's another good class. So the other good class is FPT. So those are all those parameterized problems that can be solved in time f of k times a polynomial in n. where f is some arbitrary function of the parameter only. And then we have some parameterized intractability classes. So those play kind of the role of NP in classical complexity. So if we can show that a problem is hard for one of those classes, then very probably the problem does not have an FPT algorithm. And then XP is the class of problems that can be solved in time f of k times n, not to a constant, but n to the power some function g of k. So why would we care about such running times? Well, that's what people usually call polynomial when k is a constant. So when the parameter k has a constant value, then g of k, some function of a constant, is also a constant. It might be a very large constant, but okay, it's a constant. And f of k is also a constant. So we have a constant times n to the power a constant. So that's actually polynomial when k is constant. But yeah, and so since the constant here in the degree of the polynomial depends on k, it doesn't give us a very nice running time. So when k becomes larger and larger, when k equals 20, usually this gives us prohibitively large polynomial running times. So that's why FPT is much nicer, because here this degree of the polynomial doesn't depend on k. Okay, so this is the hierarchy of classes. So we have P is included in FPT, FPT is included in W1, etc. And then at the highest level of the W classes, we have something called WP, and that's included in XP. Let's focus on FPT and let's say W1, because that's where the real break happens, where we go from classes, nice classes like P and FPT, to intractable classes like W1 and W2, etc. So it's known that if FPT is equal to W1, then the exponential time hypothesis fails. So this means then that 3-set, so the 3-set satisfiability problem, a well-known NP-hard problem, can be solved in sub-exponential time. So not just exponential time, but sub-exponential time. And it's believed that we actually need exponential time to solve 3-set. Okay, so it is unlikely that FPT equals W1. So that means that if we show that a problem is W1 hard, and we'll have a lecture on this, then the problem is very unlikely to have one of these nice algorithms where the running time or the exponential part of the running time depends only on k and not on n. Okay, let's have a look at an example. So we'll stick with vertex cover. And so our input is still a graph G on n vertices and an integer k. Let's say the parameter is k. And the question is whether G has a vertex cover of size at most k. So, and of course a vertex cover is a set of vertices C such that every edge of the graph has at least one endpoint in C. And here we have an example graph where the red vertices form a vertex cover of this graph. So we can see that for every edge in the graph, at least one endpoint is red. So if we select the red vertices, then we get a vertex cover of size 5. Okay, so my goal now is to present an FPT algorithm for vertex cover. So let's look at the algorithms we had already. So the brute force algorithm, so vertex cover is a subset problem. So in brute force, we can get a 2 to the power n time algorithm. So an O star 2 to the power n time algorithm. So that's not FPT because the exponential part here, the 2 to the power n, clearly depends on n. If we are smarter and only enumerate subsets of size k, we get that the running time depends on the number of subsets of size k. So the exponential part will be the number of subsets of size k. So there's n choose k many of those, which can be upper bounded by n to the power k. But here again, so in this exponential function, that exponential function depends on both n and k. So that's no good. So that's not an FPT algorithm. This is actually an FPT algorithm, and it's a simple algorithm. So it's called VC1. Okay, and the argument here that we get is the graph G and the integer k. Now, okay, so our graph G is, so let's say G consists of a set of vertices and a set of edges. So V is the vertex set and E is the edge set. So if the edge set is empty, so if the graph has no edges, then, well, either the graph that we got in the beginning doesn't have anything that needs to be covered, or while processing, we have now arrived at a recursive call where we have already covered all the edges. So this is a recursive algorithm. So we check whether we are done already, whether we have covered all the edges. And if so, then we return yes. We assume that k is at least 0. So that's an assumption that we make. Now, okay, if k is actually equal to 0, then, and line 1 didn't trigger, now we know that there's still some edges left to be covered, but our budget is 0, so we cannot select any vertex anymore. So we have exhausted our budget, there's still edges left to cover, so this resulted in a failed attempt, right? So now we return no. Okay, so these are our two base cases. They're very simple, so either we are done, we have covered all the edges, and the second base case is we haven't covered everything yet, but we are not allowed to select any vertex. And now, so these are our base cases, these are halting steps, and we have one single branching step. And so what does this branching step do? So it selects an edge uv in the graph. So we have two vertices, one is called u, the other one is called v. And so the algorithm now says, okay, so this edge needs to be covered. And it can be covered either by u or by v. So either we add u to our vertex cover or we add v to the vertex cover. And these are our two options. So if we add u to the vertex cover, what happens then? So u is some vertex in our graph, and if we add it to the vertex cover, now this covers all the edges that are incident to u. In particular the edge uv, but others as well, right? Okay, so now what does this operation do? So g minus u, it deletes u from the graph, and well, this implicitly also deletes all edges that are incident to u. So basically we get the following graph. So we still have v, we still have all the other neighbors of u. So this one is still there, this one is still there, and this one is still there, but u has disappeared. And our budget has now decreased by 1 because we already added like u to the vertex cover. And what remains to be done is we need to cover all the remaining edges that u didn't cover. So we need to find a vertex cover of size k minus 1. Our budget has decreased by 1 in the graph g minus u. And the graph g minus u contains all the remaining edges that need to be covered still. So that's the first option. And the second option is that we just add V to the vertex cover. So same thing, we delete V from the graph and decrease the budget by 1. Okay, so we consider these two possibilities. So either we add U to the vertex cover or we add V to the vertex cover. And then basically the G minus U and K minus 1 tells us what still needs to be covered when we do this. So if either of these two returns yes, then we return yes. So if there's a vertex cover of size K that contains U, it means that there's a vertex cover of size K minus 1 of G minus U, then we return yes. And also if there's a vertex cover of size K that contains V, then we also return yes. So if either of those returns yes, then we return yes. Otherwise, we return no. Okay, so I said this is an FPT algorithm. So I said that we can upper bound the running time by something where the exponential function depends only on k. So why is this? So let's look at an arbitrary execution of the algorithm. So what happens? So we have so G comma K is our input. And let's say, so we have a node here that it represents a recursive call of the algorithm. So it does some simple checks, right? So our algorithm just checks whether the edge set is empty and whether K is at most 0, and then it determines an answer right away, or it selects an edge UV, and all of this can be done in polynomial time. And the only thing that takes exponential time is actually the size of this search tree. So the recursive calls, so the number of recursive calls determines the running time of the algorithm. Okay, so what does our algorithm do? So it selects some edge UV, and then either it adds U to the vertex cover C, or it adds V to the vertex cover C. And now we get in both of these recursive calls, we get some two different graphs. So the instance here is G minus U, and the parameter is K minus 1. And here we have G minus V, and the parameter is also K minus 1. Okay, and so this goes on. So maybe this one makes further recursive calls, this one as well, and here, let me just record the parameter. The parameter becomes K minus 2 at this level. Maybe some of these branches terminate, but how long can this go on? So it goes on until when k equals 0, then we are done for sure, because we will not have a branching when k becomes 0 because of lines 3 and 4. So this means that, well, the height of the search tree here is at most, let's say, k plus 1. Okay. And so on the first level of the search tree, on the uppermost level, we have one node. On the second level of the search tree, we have two nodes. On the third level, we have 4 nodes, etc. So at level number I, we have, well, 1 is equal to 2 to the power 0, 2 is equal to 2 to the power 1, 4 is equal to 2 to the power 4. So the number of nodes always doubles. So from one level to the next, the number of nodes doubles. And that's why, so at the last level, we actually have at most 2 to the power k nodes. So what does that mean? So the number of leaves of our search tree is at most 2 to the power k. Okay, since this is a binary tree, we know that if we have 2 to the power k leaves, then the number of internal nodes is at most 2 to the power k minus 1. We can easily prove this by induction. I'll let you do it. But if we have some number of leaves in a binary tree, then the number of internal nodes is 1 less than that. And then at each node of this tree, the algorithm only spends polynomial time. So in total, the running time is, well, we have 2 to the power k leaves. We have 2 to the power k minus 1 internal nodes. And at each of these vertices of the search tree, we spend polynomial time. Okay, and so what is this? So this is 2 times 2 to the k. We can ignore the minus 1 times n to the power of 1. And of course 2 is just a constant. And then we get a running time of O star of 2 to the power k. Okay, so actually the running time that we had listed here, 2 to the k times n, is actually feasible for vertex cover. And one can actually get faster algorithms than 2 to the power k. Okay, so we proved already that we can get a running time of O star 2 to the power k for vertex cover. Let's briefly think about whether we can get something faster. So what did we exploit here? We exploited the fact that if we have an edge in our graph, then one of the two endpoints at least must be in the vertex cover. But now, if we actually look at so vertex u again, so it had v as a neighbor, but it had other neighbors as well, right? So we said that either we add u to the vertex cover, or we add its neighbor. We can now say something a bit stronger, namely that either we add u to the vertex cover, or we don't. Okay, so if we don't add u to the vertex cover, who is going to cover its incident edges? So for these to be covered, if u is not in the vertex cover, then actually all the neighbors of u must be in the vertex cover. So we can branch into two cases now. So either u is in the cover, or so u is not in the cover, but then all the neighbors of u, and we write this n of u with round brackets, so they must be in the vertex cover. Okay, so why is this useful? Because u could just have one neighbor, and then we don't get anything better than what we had before, right? But if u has only one neighbor, actually we can do something better, because why would we add u to the vertex cover? The neighbor covers all the edges that u covers, plus maybe more. So maybe adding u to the vertex cover, if it has degree 1, is not a good choice. And we can even go further. So this is the second algorithm. So the first 4 lines are the same as for the first algorithm. So if we have covered all the edges, then we're done. If our budget has become 0, then we are done. If the maximum degree of G, so this delta here, that's the maximum degree of G, so the largest degree of a vertex in G, if that one is at most 2, then we can solve the problem in polynomial time. And otherwise, we can now not select an arbitrary vertex, but select a vertex with maximum degree. Because, so here we make most progress when U has high degree, because then in the second branch we add many vertices to the vertex cover, and so our K decreases by a larger amount. So we make more progress, and that's why the algorithm should have faster running time. Okay, so that's what we do. So if the maximum degree is at most 2, we call a polynomial time subroutine to solve the problem. Otherwise, we select a vertex with degree at least 3, or one of maximum degree. And now we either add this vertex v into the vertex cover and decrease k by 1, or in the second option here, we actually add all the neighbors of v into the vertex cover. So the neighborhood of v with round brackets goes into the vertex cover. So those are the neighbors of v. But what we delete from the graph is the closed neighborhood of v. So the closed neighborhood of v, written with square brackets, includes v and all its neighbors. So we can also remove v from the graph because it doesn't have any incident edges anymore after we deleted its neighbors. So we can delete v and all its neighbors. But k decreases only by the number of neighbors. So if v has degree 3, k decreases by 3, but we actually delete 4 vertices from the graph. So we put 3 of them into the vertex cover. Now we get an isolated vertex. V becomes an isolated vertex that we delete as well. Okay, so what's the number of leaves of any search tree corresponding to an execution of that algorithm? So we know now that, well, in one branch, k decreases by 1, and in the other branch, it decreases by at least 3. We'll go more into details about how to upper bound such running times later in the course, but let me just give you a teaser. So we can write this T of k, which represents the number of leaves of the search tree, as x to the power k, because we know we get an exponential number of leaves, so let's write it as x to the power k. So this is then at most x to the power k minus 1 plus x to the power k minus 3. Now what I'm doing here is I divide everything by x to the power k minus 3. And then I get x to the power 3 on the left, and well, what was on the right, I take it to the left, so it gets we get a minus x squared minus 1 should be at most 0. And now we can solve this equation that we get. So we get x cubed minus x squared minus 1 is equal to 0. So that equation has a unique positive real solution, which is roughly 1.4655. And then we get a running time, or our number of leaves of the search tree is now upper bounded by x to the power k. And So that means that the number of vertices of the search tree is also upper bounded by a function of this. And we get a running time that's 1.4656 to the power k times the polynomial in n. So we rounded the last digit up because, well, there's some missing digits here. So we cannot actually claim that the running time is 1.4655 to the power k. Mathematically, this would be incorrect because it's more than that. But if we round it up, we are allowed to state the running time like this. So our second algorithm now has a running time that's O star of 1.4656 to the power k. Okay. And so there's some further reading that you can do about introductions to both exponential time algorithms and parameterized algorithms. Let me quickly show you the references. They will all be in the lecture notes.